Hello everyone, welcome to this video. In this video we shall be talking about generalized coordinates. So the smallest possible number of variables which are used to define the configuration of the system, which would be the topic for our next video. So the smallest possible number of variables which are used to define the configuration of the system are known as generalized coordinates. For example, earlier we are more comfortable using Cartesian coordinates, which are x, y, z in 3 dimensions, right? But in several situations, these coordinates, the Cartesian coordinates, they are not convenient to use because of some kind of geometry. For example, you have a cylindrical geometry or you have a spherical geometry, right? So we are also familiar with these kind of coordinates, right? Cylindrical coordinates, these are represented by rho, phi and z, and spherical coordinates, they are represented by r, theta and phi, right? Moreover, in addition to these, for having different set of coordinates, we can also describe the motion of any system where the coordinate system is itself moving. So in that case, it would be really difficult to note the motion in the usual Cartesian coordinates. So for that, what we do is we define a set of generalized coordinates, which could be any set of coordinates which is capable of describing the whole configuration of the system. That means you, with those coordinates, you can completely define the motion and state of that, the configuration of that particular system, right? In fact, all sort of quantities may serve as generalized coordinates. For example, we know how to write the Fourier series expansion of any function, any piecewise function. So when we expand any function as the into a series of sine and cos, right? So whatever is the amplitude or the coefficient of several terms in that expansion, we can also take these quantities to be the generalized coordinates. Moreover, in a double pendulum, what is that? It is simply that one bob is attached to this string over here, right? Moreover, another bob, this one, is attached to this one through this rod. So the motion of this bob is due to this length, right? And the motion of this bob is due to this bob. So here in this case, the vertical angles made by this rod and the bob, right? Here theta 1 and theta 2, they can also serve as generalized coordinates. Moreover, if you take any simple pendulum, then the motion of this pendulum from this mean position, this distance, this can also serve as the generalized coordinate to describe the system of this pendulum, right? Moreover, the quantities which have the dimensions of energy, angular momentum or time, they can also serve as generalized coordinates. So according to our need, we can choose the generalized coordinates, right? So the notation for generalized coordinate, we generally represent it by Q, right? And for n generalized coordinates, we use the subscripts 1, 2 up to small n, right? So the generalized n coordinates, they become Q1, Q2 up to Qn. So let us look at some of the systems which we already know. Let us quickly revise that. So the first system you can see here on the left is that of the Cartesian coordinates. That means it has x, y and z components. The second represents the spherical polar coordinates, having coordinates as r, theta and phi. The third one is representing the cylindrical coordinates, having coordinates as rho, phi and z, right? So these are the coordinates over here. This is the cylindrical system. This is the spherical polar coordinate system, and this one you know, that is the Cartesian coordinates, right? So if you want to transform this system to the second system, you need a transformation, and we all know what transformation is this. This is the transformation. So basically any point over here represented by this x, y and z now can be represented by r, theta and phi, where what is this r? R is the distance of the point from the origin O, right? And what is this theta? Theta is the angle made by this r with the z-axis. And what is phi? Phi is the projection of this point over to xy plane and its angle with x-axis, right? So we have these transformations in this case. Moreover, in this case, we assume that the body is cylindrical in nature and it is aligned towards the z-axis, like it is in z direction. So this z, the coordinate z is along this axis, right? And if we have any point over here, so how can we represent it? X, Y, Z coordinates would then be rho cos phi, Y would be rho sin phi, and Z would be Z itself, no changes in Z. So these are the coordinate systems. So next, if we have a coordinate system in x, y, z, that means we are talking about three-dimensional space, and we have one particular particle in that. So how do you represent that particle in that space? You represent it, I am talking about Cartesian coordinates right now, so it would be x, y and z, right? Now if you have three particles then in the same coordinate system, then it would be something like the coordinates representing these 3 points would be something like x1, y1 and z1. Second, the coordinates corresponding to second would be x2, y2, z2, and for third it would be x3, y3 and z3. So overall these many coordinates are required to describe the position of these three particles in three-dimensional Cartesian coordinate system. So similarly, if you have n particles, so you're here in this coordinate system, you have n particles, then how many coordinates do you require? You require 3n coordinates, namely x1, y1, z1, x2, y2, z2 up to xn, yn, zn. So the total number of variables required in this case, in the first case, that is 3. In the second case, we have 3 particles and we are in 3 dimensions. So the total number of particles is 3 multiplied by 3, that is 9. And now similarly in the third case, we are in 3 dimension. For defining each particle, we require 3 coordinates. For defining n particles, we require 3n coordinates. Therefore, the total number of variables which are required in this case are 3n, right? So, in terms of generalized coordinates, how do we write them? For 3 particles, it is q1, q2 and q3. That is, we start with the subscript 1 and end with the number of variables that we have. In this case, it would be q1, q2 up to q9, right? Because the total number of variables should be 9, and in this case, it should be q1, q2 up to q3n, right? So we have total 3n number of generalized coordinates to represent this system of particles in 3 dimensions. So that is it for this video. Thank you for watching.